Hello again. Today we're going to talk about limit techniques. So this is going to be more limit problems, showing you some problems that you can have with trying to evaluate a limit and what techniques you can use in order to solve those problems. Okay, so for example, if you're trying to do a limit that involves a fraction, like let's say we have the limit as x approaches 1 of x squared minus 1 over x minus 1. If we just try to use the limit rules from the last video, you'd evaluate the limit of the top, limit of the bottom. They're both polynomials, so you just plug in 1 into the top and 1 into the bottom, and you get 0 divided by 0. Now, division by 0 is not allowed, but when it comes to limit problems, when you have specifically 0 over 0, sometimes you can actually get a result back out by using some techniques. If we simplify the expression on top, we can factor that out into x minus 1 times x plus 1. Then you can cancel the x minus 1s on the top and the bottom, just leaving the x plus 1. And then the limit of, as x approaches 1 of x plus 1, that's a polynomial, so you just plug in 1 and you get 2. So final answer is 2. Okay, so this limit, which originally we can call a 0 over 0 limit, ended up equaling 2. Now, does that mean that every single limit that is 0 over 0 is 2? No. Okay. 0 over 0 is something called an indeterminate form. An indeterminate form is one in which you cannot tell what the final answer is just based on the form alone. You need to do more work. So whenever you see a 0 over 0 problem, you're going to have to do some sort of technique, like in this case, factoring and canceling, before you can get the final answer. Okay. Now, there is some things I want to explain. As I've said, 0 over 0 could give you 2, or it could give you some other results. So let's look at another problem. Okay, let's make the limit go to 4 this time. And I'm going to put x minus 4 on top, and maybe x squared minus 3x minus 4 on bottom. Okay. And if you were to plug in 4 to the top, you get 0. And if you were to plug in 4 to the bottom, you get 16 minus 12 minus 4, which adds up to be 0. So we have 0 over 0 once again. And once again, we can factor that denominator. So let's do that. We can factor the denominator into x minus 4 times x plus 1. And once again, like last time, we can cancel off the x minus 4s on the top and bottom. Now that's going to leave you a 1 on top. And now if you plug in 4, you get 1/5. So as you see, 0 over 0 could wind up being any number. And it's hard to know what that number is until you do some sort of simplification. Okay? Let's look at another 0 over 0 problem. And this one's going to be a lot simpler. Okay, what if we had the limit as x approaches 0 of x over x squared? Okay. Actually, I'm going to restrict that and make it limit as x approaches 0 from the right. Okay. Well, you can get rid of an x on the top and bottom, factoring. And then we wind up with the limit as x approaches 0 from the right of 1 over x. So we have the top is a constant and the bottom is approaching 0. So instead of 0 over 0, we now have a constant over 0. When you have a rational function like this that is a constant, like the top's approaching constant, the bottom's approaching 0, then this is going to wind up approaching either plus or minus infinity. And that's because rational functions have vertical asymptotes whenever the denominator approaches 0. So this has a vertical asymptote at x equals 0. In fact, if you look at the graph of y equals 1 over x, which looks like this, you can see that as x approaches 0 from the right-hand side, we go up towards positive infinity. And the graph shows why I did it from the right instead of from the left or in general, because those are three different answers. If we were to change this problem and do the limit as x approaches 0 from the left, we're now approaching 0 from the left-hand side, which plunges down to negative infinity. And if I hadn't chosen left or right, and I just did the double-sided limit, just x approaches 0, then you need to look at the left and the right, and they're going to two different infinities, and therefore the limit does not exist. So, as you can see, something that is originally going to 0 over 0 could wind up being a constant, like the first two examples, could wind up being positive infinity or negative infinity, or it could even wind up not existing. So just reinforcing, when you have 0 over 0, which is an indeterminate case, and we will have some more indeterminate cases later, you don't know the answer immediately, and you have to do some form of simplification first, okay? Okay, let's look at another problem that we will have to use another technique to solve, okay? Let's say that we have a limit as x approaches 2 of x minus 2 over, we'll just do square root of x minus square root of 2. Okay, so as x approaches 2, if you were to plug 2 into the top, because it's a polynomial, that's going to go to 0. And the bottom, using various limit rules, essentially you plug in 2 and you also get 0. So we have 0 over 0, which we know is indeterminate, so we need to do some more work. Okay, so what can we do? We can't factor this, not in the traditional sense. We have to use a technique specific to square roots, which is multiplying by the conjugate of the expression with square roots in it. The conjugate of square root of x minus 2 is square root of x plus 2. I'm assuming that you're a little familiar with conjugates. So we're just going to multiply that times the top and the bottom and simplify. Okay. Actually, let's just leave the top factored because it would be a real mess if you were to multiply these two things together, and I don't think it's necessary. But in the bottom, you do want to multiply those two together because they're designed to sort of cancel and get rid of your square roots. Foiling, square root of x times square root of x is just x. The inner is minus root 2 times square root of x, and then the outer is plus root 2 times square root of x. So those are opposites, and they add up to be 0, so they cancel. And then this times this, the lasts, minus root 2 times root 2 just gives us minus 2. Ah, that's convenient because now the denominator, x minus 2, is the same as that factor on top. So we can cancel those two factors, just leaving square root of x plus square root of 2. So now if you plug in 2, you get square root of 2 plus another square root of 2, which is 2 square roots of 2. Okay, so this is yet another technique that you sometimes have to use when you have square roots, which is to multiply by the conjugate. That will usually produce a factor that you can then cancel out with something on the other side of the fraction. And the square roots could appear in the bottom like this problem, or they could appear in the top. Doesn't really matter. You're going to want to multiply by the conjugate of the expression that contains the square root. Okay. Another technique that you'll sometimes have to use is one where you have an expression that contains a fraction on the top or the bottom of the main fraction. So it's like a fraction inside of a fraction, okay? Or I think it's sometimes called a complicated fraction. whatever you want to name it. Okay, so let's say that we have the limit as x approaches 2 of 1 over x minus 1/2 all over x squared minus 4. Okay, so plug 2 into the top, you get 1/2 minus 1/2, that's going to go to 0. Plugging 2 into the bottom just gives you 0. So we once again have 0 over 0. Okay, and we can factor the bottom, but then nothing's going to cancel with the top yet. So we need to use some other technique to get something that will cancel, because that's what usually is the last step before you can evaluate your limit, is finding something that you can cancel, and then it'll be simple enough to just evaluate the limit. Okay, the thing we want to do here is to get rid of these fractions on the top of the main fraction, and the quickest way to do that is to find the least common denominator of these two denominators, and since they have no factors in common, it's just going to be 2 times x. And then instead of finding the least common denominator and combining those two together into one fraction, a quicker way is just to multiply by that least common denominator you found on the top and bottom of the main fraction. Okay, so 2x times 1 over x gives you 2x divided by x, which is 2. And then 1/2 times 2x gives you just x. So 2 minus x is what you get on top. On bottom, it's best to leave this factored. In fact, I want to factor that as well. So we get x minus 2 times x plus 2, because this is a difference of 2 squares. And this is times 2x. Now, you may not immediately see two factors that cancel, but you need to remember that 2 minus x and x minus 2, those are just reversals of each other. Like you can factor out a minus 1 out of the top and rewrite that as minus 1 times x minus 2. See, therefore, it's the opposite of that other x minus 2. And then you can cancel out the x minus 2's. Okay, and then canceling and cleaning it up, we get the limit as x approaches 2 of -1 over 2x times x plus 2. Now we simply plug in 2 into that. The denominator would become 4 times 4 is 16. So minus 1/16 is the final answer. Okay, so this limit technique was finding the least common denominator of all of your denominators, and then just multiplying that on top and bottom to get rid of the little fractions that were on top or bottom of the main fraction. And then canceling, like I said before, it's usually the last step before you can evaluate it. And then the last step was just evaluating it, which is just using limit properties, realizing the bottom's really a polynomial, you just plug in the number. Okay. Now, I think these are the 3 major techniques. So factoring and canceling, using conjugates, and simplifying more complicated fractional problems. And you could even have problems which require you to use multiple of these steps. Let's do one more problem at least. Okay, so let's look at this problem. If x approaches 1, we would have 4 over 0. Okay, that's weird because, we can't have division by 0. It breaks one of our limit laws. But I told you earlier that when you have something that approaches a constant over 0, that's because it's at a vertical asymptote of the graph. And so this might be approaching plus infinity or minus infinity, depending on which side of the graph you're approaching. And this has the exact same problem. If you plug in 1, you'd get a 4 over 0. Okay? So this is something that is another indeterminate form. It's an indeterminate form of the form infinity minus infinity. Okay? And we're going to simplify this time by combining the two fractions together into one fraction And then we can use some of our other techniques of canceling, usually on the top and bottom. And I think eventually we're going to get an answer that isn't just going to be, does not exist. Okay, so I need to get a common denominator. Well, these two factors are the same, so I just need this other factor added in. So it's just going to be x times x minus 1 is the least common denominator. So we want to change these fractions so that both have that denominator. There's nothing we have to do to this one, but this one we have to introduce an extra x into the bottom. So we multiply x on the bottom, and therefore we'd have to multiply by x on the top. Okay, and then we just write the other fraction. Now that the two fractions have the same denominator, you can then add them together by just adding the tops together. Okay, then you may see that we have, we can factor out 4 out of the top, leaving x minus 1. The x minus 1s would then cancel on the top and bottom, therefore just leaving 4 over x. And then plug in 1, and your final answer is 4. So this, once again, was another indeterminate form, infinity minus infinity, and we wound up simplifying it and just getting the number 4. Okay, usually exploration of indeterminate forms is covered a little bit later in the course after you learn about derivatives, because it turns out that there's 7 different indeterminate forms, and at least 3 or 4 of them are too complicated to talk about before you learn derivatives. We'll have a way to evaluate all of the indeterminate forms using derivatives. But even now, some indeterminate forms you can solve simply by doing some of the limit techniques. Let me explain what indeterminate forms we can solve right now, and I'll do a couple of more examples of the last couple of indeterminate forms. All right, so for right now, we'll just be talking about these 4 indeterminate forms: 0 over 0, infinity over infinity, 0 times infinity, and infinity minus infinity. And we've already done some problems that are 0 over 0, and we just did an infinity minus infinity, but we haven't, I think, done a problem involving infinity over infinity or 0 times infinity. So let's look at one of those. I think I'll try to design a problem that is a 0 times infinity problem. All right, here's an example of a problem that is 0 times infinity. Although, really, we could just combine this together by moving x minus 4 onto the top. And then it becomes really a 0 over 0 problem, but that's okay. Think of this as just another practice problem. On this one, because we have a square root, we would simplify by using the conjugate, which was going to be square root of x plus 2. So multiply that on the top and the bottom. The top just leave factored. Bottom, foiling it out, gives you x minus 4. The x minus 4s are going to cancel, leaving the limit as x approaches 4 of root x plus 2. And then if you plug in 4, you get 2 plus 2. So final answer is 4. Okay, so this was a pretty simple example of a 0 times infinity situation. Okay, so I think that's going to be it for now for limit techniques. The next video is going to talk about one very, very specific limit technique called the squeeze theorem. which will allow you to solve certain limit problems. And it's especially useful for problems involving trigonometric functions, which we haven't done an example of any trig functions yet. We've been sticking mostly to, polynomials, rational expression, roots and fractions, things like that. But next time we'll be tackling some limit problems that involve sine and cosine, and the squeeze theorem is going to help out with that. Anyway, that's it for this video. Have a good day.